talk of the seminar, last invited talk of the seminar. Ricardo, let me introduce Ricardo. Ricardo is a professor in the computer science and electronic engineering department at Essex University. His main research interests include brain-computer interface, brain cognitive augmentation, neural engineering, genetic programming, particle swarm optimization, and the theory of evolutionary algorithms. He has published more than 300 reference papers on evolutionary algorithms, biomedical engineering, neural networks, and image signal processing. He was co-founder of the Essex Brain-Computer Interface Lab in 2004, and he has co-authored the books Foundations of Genetic Programming, a field guide to genetic programming. And I'm sure that you have another book on evolutionary computation that it is not listed on this web. On the official, he has been, he co-chair of numerous international conferences. And sorry for it, it's outdated this info. I know that you have another book and more things, but I leave you.
Face, I guess this is the. So I will need to allow. Just give me a second. Google Chrome to access. The facilities, allow for Mario, whatever. I need to. Do I need to quickly reopen? Google may not be for the content of the screen, so I might need to. So I'll try to share. If that doesn't work, I need to go quit and reconnect. I'm sorry, I wasn't aware of this.
It's all right. It's all right. If you haven't shared with Chrome lately, then you have to log out and log in again.
Just what share. Well, I'm not sure it actually is. I think I need to log out and come back in. Sorry.
No, it's all right.
Buenos días a todos.
En un momento empezamos.
So can you hear me okay?
Sorry?
Can you hear me?
Yes, we can hear you.
Let me try to share the screen. Window the entire screen I want to share. And it says insisting that I should enable. I already enabled this. So I don't. No, it's not working. So I'll try to only share one window there. PowerPoint.
Yes.
Oh God, we really didn't need this one. Select the tab to share. Okay. Share the window. You need to restart Chrome, which I did. I thought I'd had. So again, I'll need to log out and close Chrome. Sorry.
It's all right. Don't worry.
¿Puede reiniciar la computadora?
Yo me tenía que reiniciar.
María, ¿no quieres jugar una casita?
¿Vale?
Una casita.
¿Que si quieres una casa?
Okay, so I will try again. Yeah, I think I can.
The third one is the good one.
Okay, yeah, hopefully. Okay. Okay.
You see? It was the good one.
Yes. Okay, so you can see my slides. Can you?
Yes.
Can you see the slides? Okay. So thank you and sorry for the delay. Let me check the time. Okay, about 5 minutes late. And so obviously I'm going to talk about evolutionary algorithms, but as more like the connecting line between other elements that relate to neural networks, in particular the vanishing gradients problem and and some ways of assessing, fair ways of assessing the performance of machine learning algorithms, and also to guide AutoML algorithms. And this is work that I've done in collaboration with Ahmed Yilmaz, who was a PhD student and been a collaborator since then on working on evolution of neural network learning rules and other problems. So what I'm going to talk about is the good old-fashioned ways of doing neural networks. Good old-fashioned means sigmoid activation function, initialization with zero mean and small standard deviation, small learning rates, and then the standard gradient descent by plus error backpropagation to calculate the derivatives. And then I will use as a performance measure the good old-fashioned loss and or accuracy, or even in some problems the total square sum of the errors. So the layers, the networks will be organized in layers like this, will be shallow, not very wide, and some input features, and one more output neurons, of course. So I want to just spend a second on the vanishing gradient problem. So basically the story is that by error backpropagation, of course, the amount of change produced to the weights and the biases is proportional to a component of the gradient. Now, and this in deep neural networks reduces very quickly to tiny amounts. The gradients become prematurely small. I would say they start prematurely small. And then, of course, because the changes are very, very small, then that leads to essentially freezing the biases and weights of the network. And so that basically the error never comes down. And here I have an example on the right here. Let me enable my laser pointer here. Of the iris classification problem, which is an easy problem, really. And in this problem, however, I was using a network with 10 hidden layers, and this is the layer number. And here are the number of epochs on a logarithmic scale. But what you can see is that the biggest gradients are at the output, as you kind of would expect, and then the decrease. But the decrease is very, very quick, very sharp, again, logarithmic scale. So when you get, by the time you get to the input layer, the layer connecting inputs to the first hidden layer, actually those gradients, the magnitude of the delta weights, the changes, are incredibly small, something like 10 to the minus 13. And they don't seem to change by much, if not by decreasing down to nothing. Now, obviously, with such small changes, unavoidably, you have tiny, tiny little changes to the weights, and basically you can be stuck forever. So, okay, so that's just to create the background for my presentation. I also want to just remind people, most people will know what a genetic algorithm is, but it's a very tiny tutorial on a genetic algorithm. This is a steady state genetic algorithm. You start from a population of random tentative solutions, and this algorithm typically arrays of numbers. Each individual is an array of numbers. Then you evaluate the fitness or quality of each individual, and then you start the loop of creating offspring by either crossover, preceded by selection of fitter than average individuals from the population, or by mutation, again selected, preceded by the selection of one above average parent from the population. So then, of course, you have a new individual. You need to evaluate the fitness of it, the quality, and then you, in this particular algorithm, you replace some individual from the population that wasn't very good, and you keep going, iterating. Now, I also want to briefly introduce genetic programming, but a very special version of it, which is register-based genetic programming, because it's really essentially very much like a GA. So instead of having an array of numbers, an individual would be an array of instructions, which could actually be numbers, because there could be the opcodes for these instructions. And these are instructions for a really a low-level machine, a register-based machine, where you, in this case, you have a register 0, register 1, and you do an operation overwriting whatever is on the other register on the left. Plus, you have some assignment of constants. It could be 0.1 minus 0.1, plus 0.5, and so on. Assignment to the register so that those constants can become part of the calculation. And there are many more instructions typically, but you must have also some input registers that carry into the calculation some information about the problem, the input, for instance, of the fitness case, it's called. Typically, these registers are protected, so they can never be on the left-hand side, so that they don't get overwritten, and the information is available everywhere. Now, typically, evaluating fitness in a genetic programming system like this one requires running the program multiple times on each, as we call it, as a fitness case. And each time you need to load the input registers with some value, in this case, it's just one, and then execute the program instruction after instruction, and then read out the result. And typically it's this register 0, which essentially acts like an accumulator. So you put some inputs, execute, read the output. And then once you've done this for many cases, you are in a position to decide whether the output are more or less what you wanted or not, to what degree. So you can essentially evaluate the fitness of that program. Now, we wanted to use genetic programming, this form of genetic programming, to evolve general learning rules for neural networks, for the good old-fashioned neural networks that I showed you before. Now, we tried this with Amradi, another PhD of mine, when I was still at the University of Birmingham. That's a quarter of a century ago, basically, in the late 90s. And the problem we had back then is that we couldn't be sure. The amount of computation that we could devote then was way less, and we couldn't be provably able to show that the rules were general and they were applicable to sorts of situations. So in this case, obviously, to do this problem, you need to have a bigger set of instructions, as shown here. You also have a no-op operation that doesn't do anything. So that allows the production of programs of variable length within a structure of fixed length, which is the chromosome, so to speak. Now, in addition to these various constant assignments that we have, change of signs and operations of various types, but we also have 4 different input registers. This register that contains activations, it contains activation of the current layer, the array prev, the previous layer activations, and then we have an error register that can be actually the error at the output, if it's talking about an output neuron, if J is an output neuron, or the backpropagated error from the previous layers if it's an internal neuron. And then we also provided this SBP. SBP stands for standard backpropagation. And so we provided exactly the formula for computing the gradients, essentially. So in here, for each weight and bias in the network, you would have the component of the gradient computed through the traditional method, which is this calculation here. Now, as an output, we have the register 0, which we directly used to produce the change to be applied to the corresponding weight. Now, the fitness, of course, is a form of loss, error, basically. We want to minimize it. But what is important is that you really need to execute programs in lots of cases if you want to evolve general learning rules. So you need to go through each problem that you have selected to be in your training set for the GP system. You need to go through the different seeds that produce random initializations, so across multiple initializations, and then you need to iterate the rule for every single epoch in a run. And then you also need to go through every single weight, and you have another for loop over every single instruction. So you understand why, of course, we had to use relatively simple problems, relatively small networks, relatively few seeds, etc. So we considered only 2 training problems, the parity problem, which is a Boolean problem, so outputs are zeros and ones, and the iris problem, where it has multiple classes, 3 classes, and it's a continuous problem. The features are continuous. But incredibly small network here, 2 hidden layers, 2 neurons for this problem. Told you it's easy. And with 5, a network with 2 hidden layers, each with 5 neurons for the other problem. And different learning rates, which are appropriate for those problems, and 4 different initializations for each. Programs were small, they're up to 30 instructions, but because there were no op operations, it could have been a lot less, a lot shorter than that. And also population sizes were small for standard in genetic programming, that is 400 individuals. And runs were reasonable length, so 100 generations. But what matters here is this number. So the multi-product of these 2, which tells you how many fitness evaluation you do to evolve a new learning rule. Now, this number is very small compared with other efforts that have been recently done in the literature. And I won't mention Google. Oops, I mentioned Google. Okay, so we've performed 20 separate runs of this system, and each dot in this diagram is a run plus the standard backpropagation as a reference. Now, in this direction here, we have, sorry, I don't know why there is a little thing in there, but along this axis, we've got the number of instructions. From 1 instruction, if you have just an RA, RSPP register, to up to 30 instructions up here. And on this axis here, we have by how much better the error is with respect to the error made by the standard backpropagation alone. So anything that is on the right, this part here, any dot that is on this side of the diagram is a rule that is better than the standard backpropagation on those problems that were in the network architectures, but not on the same seed, on 50 different initializations. So each dot is an average across 50 different initializations. So we wanted to be sure that we're not overfitting the initial seeds. And so basically 17 out of the 20 runs, only 3 failed, were able to produce a better learning rule than the standard backpropagation for those problems. Now, of course, this is like a Pareto diagram, and of course there are non-dominated solutions, which are the ones in red here, which are all better than the others, either by improvement over the standard backpropagation. This is twice as small, the error, for instance, here, or by the size of the rules above it. So we chose this particular rule because it was very small, 7 instructions, and it was 1.5 times better than the standard backpropagation in terms of error. So that's the rule that we will study here. So what does the standard backpropagation then looks like? Well, it's the SBP gradient produced by the backpropagation times a scalar, which is eta, which is the learning rate, essentially. Now, the new rule evolved by GP, that rule, once we've simplified it a little, but not without approximation, just algebra. Then the new learning rule is essentially the same. You've got the same eta here. You've got the same measure of gradient coming from here, but then you have a term in the middle, another eta, A, which A stands for adaptive. In other words, we found that the new learning rule was essentially an adaptive version of the backpropagation, the gradients basically, where the activation of the postsynaptic neuron, the current neuron, and the activation of the neuron just before, the presynaptic neuron, were quite important. And in addition, there was a little element of the gradient itself in it, so which is kind of counterintuitive. But so essentially, so we have some strange asymmetries in this learning rate, this adaptive element of the rule, which are, for instance, that if at the beginning of a execution, epoch 1 or 0 or 2 or 3, you might have big errors, big gradients somewhere. And then if the gradients ever become big, they could be bigger than the activations here. In other words, If it's positive, that doesn't make a big problem. But if it's a negative gradient, then it could become that the ether is negative, which would mean that our new rule makes a gradient ascent step. Perhaps very rarely, we saw that it's rare, but it can do it, which is an asymmetric and unusual move. The other thing you can notice immediately is that many of you will know that the biases are normally dealt with or are considered to be like connections to neurons that are always active. They're always one. So for this quantity here is always one. So you can see how, and these on average at the beginning it's 0.5. So you can see how biases have got a 3.5 times bigger than normal learning rate, at least at the beginning, but also they keep having it quite big later on as well, up to 2 times bigger than normal. So that's another difference with the backpropagation algorithm. And finally, when this is small enough, and quite often it's rapidly small, the gradient is small, then you have that this learning rate is essentially modulated by these 2 activations. And it's bigger when both neurons, both the presynaptic and the postsynaptic neuron are big, while it can be very small if they're quite inactive. So there is essentially an element of Hebbian learning in this rule, which we didn't really expect. Okay, you might say, fine, it's learned to solve the parity and the iris, but how about unseen problems and bigger networks? So obviously we had to go there and test it. And I think these diagrams, they all report an axis that is the p-value. And if you look at this line, whenever it goes above the 0.05 level, which is about here, it will be non-statistically significant. So in most cases, you'll see the diagrams will have a large amount of statistical significance, where one rule, the new learning rule, is better than the other. Now here, the network is the 7-segment Boolean problem. It's unusual because it's got 7 outputs, Boolean outputs, and it's not easy, an easy problem, but we can see that both in accuracy and loss, the orange line, the new learning rule is better. Now, this is 2 hidden layers, 5 neurons in the hidden layer, so pretty small network, shallow and narrow. Multiplexer, another Boolean problem, again, same picture, the orange is better. The wine classification problem, we see a slight crossover here, where for the first 25 iterations, the new learning rule is worse, and then it becomes better. And here we have a similar situation, again, with the accuracies and both validation and training. Bit bigger network here, still not very big. This is also the authorship problem, a bigger problem. Still 2 hidden layers, but 30 neurons in each. And here is quite impressive to see that both in loss and in accuracy, these 2 red curves represent the training and validation accuracy. They're way better than the standard backpropagation. Breast cancer, similar story, but quite interesting that in most runs, you would have and we're talking about averages over 200 runs in each of these cases. You would see that the loss is way better for a long, long time, and also the accuracy is way better for a long, long time, possibly remaining so up to 5,000 iterations. So this network had 3 hidden layers, still not deep, of course. And then E. coli, similar situation. Again, look, the orange curve is very, very quickly goes very down, and the accuracy is very quick. And then it remains superior. It's not very visible here. The orange line is superior to the other line, and also the red line, which is the validation. DNA, this is bigger, 3 layers and 100 neurons in each layer. Same picture, essentially. So that was reassuring, but, we might say, wait a minute, did we cheat? Did we compare the rules fairly? For instance, we've seen at the beginning that the learning rate is adaptive learning rate can be a lot bigger. It can be on average twice as big as the learning rate for the standard backpropagation. So is that fair? And, you know, so how do we set those learning rates? And what about the number of epochs? Had we continued the runs for longer? What would have happened, etc.? So the question is fairness of comparison. And actually, you might be surprised, but it's not such an easy question to answer. You need to explicitly say what fair means. And just so that people are sure, yes, it was a fair comparison, but you need to listen on a bit longer to see why it was a fair comparison. So here are some dilemmas. If I asked you which learning rule is better, the red one or the blue one? You got the accuracy here, you got the epochs. It is not random, right? The blue is definitely better than the red. I think most people would say that, which is fair enough. But what if instead of epochs here, I had a computational cost, it's in flops times, so it's petaflops, 10 to the 12, and one with a lot of zeros. And we're not talking about 1 or 2 petaflops, but 800 petaflops, 1,000 petaflops, etc. So that's an enormous amount of computation, and maybe this is how much computation you have available to solve this problem. So if I asked you the question, which one is the better rule here? If this is my budget of computation, well, the blue is still at 20% accuracy. The red is at 85% accuracy. So obviously that's the better rule. But also, what if for a particular problem, I had an acceptable level of performance? This is not 100%. I don't require 100%. Maybe I just require 90% accuracy, and I'm good. Maybe it is because it's a recommender system for Netflix, and it doesn't matter if it proposes a few random movies together with all the others. It would be unnoticeable, and perhaps it will even provide some level of delight for the users. So again, in this case, perhaps if this is the acceptable level, once I reach it, I could simply say, okay, I'm done. And so again, the red is better than the blue. What about this? Okay, here I've plotted the mean, okay, here, but I've also plotted the individual runs. And what this shows is that this mean is actually the results of, a certain number of runs being really bad and a certain number of runs being really good and essentially reaching that goal. So the question here is, again, is this a bad rule or not? Because after all, if I try a few times, I should be able to actually land on one of these runs and therefore solve the problem. So what it means is that first, the bottom level here, the whiskers of the distribution of performance do matter for practitioners, but also practitioners, they don't, machine learning researchers, they compete on validation accuracy, no matter what the complexity of an architecture is, etc., no matter how many petaflops you need to expand almost. But for a practitioner, we want to achieve an acceptable level of performance with an acceptable cost. We don't care about mean results because we just need to have one run that provides the acceptable accuracy within our budget, and we can stop. So upon failure, all of us would try again running the network and trying again a few times before they give up and say, no, this is not good architecture. So we are supposed, it's not bad to perform multiple training attempts. We don't need to have the same level of performance in every single run. Okay. So how am I proposing to do this? Essentially using an old performance measure, which is new to most machine learning, but it's not new for genetic programming. And that is the performance measure that John Koza, the father of GP, essentially used in all of his books, which has been neglected, as far as I can see, outside genetic programming, which is called the computational effort measure. So let's try to understand how this works, okay? So first, I believe that we need to declare what a successful run is. So we need to decide how we stop these runs. We can't continue runs to hoping that, I'll get another little percent or fraction of a percent of inaccuracy so I can beat I can write the paper. So we need to declare, say, this is how much accuracy or loss, or validation loss, or validation accuracy I want to reach. And then I'm happy. That's a successful run. So if we're happy to declare this threshold level for success, then we can infer the success of a set of runs, which I might want to run just to succeed. So in a set of runs, then a set of runs is successful if at least one of the runs reaches the threshold level for acceptance. So, basically, the proposal is do lots of runs with different parameters, which would be the epoch number or the learning rate, and measure this function, which is the probability of reaching the accuracy, the threshold of accuracy A by a sector epoch E with the learning rate eta. What does it mean here? Well, you'll need to perform lots of runs with all different values, etc., and then compute the ratio of those with a particular set of values that solve the problem to the desired level. So, okay, this is a costly procedure, but at least you have this probability of succeeding in one run. Now, of course, the probability of failing in one run is 1 minus this probability of succeeding. And that allows us then, next page, to compute the probability of succeeding in R runs, in multiple runs, which is simply 1 minus this to the power of R. That gives you the probability of succeeding in all R runs. And then 1 minus that will tell you what the probability of succeeding at solving the problem is in R runs, in a set of R runs. Then all you have to do is to set the value for it, a value you're comfortable with. I would say I would be happy if 99%, when I try to do this problem, I'll be able to solve it with the acceptable level of accuracy A that I mentioned before. So I'm going to set this number here as 0.99. And then I solve for R. In other words, this is just a rewrite of that equation, but with this being 0.99. And what you find is that R, of course, depends on the parameters, the number of epochs, the number of the learning rate. But there is a number here, and it comes straight from this probability distribution that you estimated before. And now it tells you how many runs you need to do, how many tries you need to do to have 99% probability of success. So it's a little bit mathematical, I know, but once you have this number, then you can compute what is the total effort of your succeeding in this problem, of the number of epochs that you're doing times doing. It's just the product of the number of gradient descent steps in total, the total number of gradient descent steps that you need to spend to have 99% probability of succeeding for a given problem and with a given learning rate, rule, and etc. Now, of course, this formula depends on the number of epochs where you stop and the learning rate. But you can minimize this. You can find the values of V and eta, and it's not complex calculation. It's very simple. That give you the minimum effort. So when this is the smallest possible value. So that gives you these values. And then with those in hand, go on the previous page, you can feed them here and compute the optimal number of runs. So from this procedure, you get the optimal epochs, the optimal learning rate, the optimal number of runs to succeed. And therefore, it's an AutoML. It's a form of AutoML. It defines parameters for you that will guarantee the best performance. Where best performance now is the total effort in number of gradient descent steps that you need to perform to solve the problem with 99% success probability. Okay, was a lot here. So that's what we use for comparing the learning rules. And we defined the on accuracy rather than loss, and we took it to be 100%. So for all problems except iris, we required that by solving the problem, we required 100% accuracy. If we had accepted a lower value, it would have been different results, but we wanted to actually solve the problem completely, except for iris, because it's noisy and it can't be properly learned to 100% reliably. So yeah, so basically that's what we did. And one element is quite interesting is this computational effort, because it's the number of gradient descent steps you need to perform to solve the problem. It does not depend on the size of the data set. It doesn't depend on the size of the network. It's simply dependent on how difficult your error measure is, how difficult it is to descend to an optimum, how many gradient steps you need to do in total in multiple runs. So, okay, so we did this and we found some results. Well, the names here are slightly different. This was R prime, so the optimal number of runs. This was E, E prime, the optimal number of epochs. This is the minimum computational effort, and this was the optimal learning rate. So let's start from R, looking at the R. For this, these are all problems that were not used, of course, in the fitness evaluation, so in GP, the GP system. And we see that for several problems, the optimal number of runs is not 1. So those problems continuing to run forever may not be the best solution. You might be better off, and particularly these Boolean problems, you can see how the 7th segment in particular is extremely hard, both for the new learning rule and the standard backpropagation. But for the standard backpropagation in particular, you need to try 24 times on average to find a seed that is good enough. And you do short runs, small number of epochs, to actually be able to solve this problem. And also for some of these other bigger problems, E. coli and breast cancer, the optimal policy for the standard backpropagation is to stop after a while and restart. And that will give you higher chance of success. The other thing that is quite strange is these learning rates here. These learning rates are big. And in particular, they're quite big for the standard backpropagation, 2.3, 2.4, 2.5, 2.9. This is less big, but way bigger than normal, 0.01, etc. E. coli 1.2, 0.9 DNA. So all very, very big numbers. A bit smaller for the new learning rule because it's got its acceleration factor, the eta A. It's contributing to amplify its movements. So quite a surprise. Now, if you look at these numbers here, they tell you how difficult the problem is compared with other problems. So if we compare the same rules, like backpropagation, and we see that there are some surprises. For instance, the 7th segment is really a difficult problem, although obviously the hardest problems are breast cancer and E. coli. And most others are simple. And we see also big reductions from with the new learning rule. This is almost a third, I'd say, about a third. This is half the effort. So it seems to be an interesting measure. Now, you might think, wait a minute, this learning rate, they're too big. They can't be real, right? So it's probably an artifact of your computational effort, AutoML thing, etc. So, okay, fair point. So I took a standard optimizer, scalar tuner with Bayesian optimization, and I ran it but I was optimizing the epoch number, stopping epoch, the learning rate, and that was it. And just 2 parameters. And I plot here the best out of 100, the top 10 performing results. And these are the averages those. And you can see that for segment, we have a 2 for the standard backpropagation, not the new rule. 2.52 learning rate. Well, let's have a look at the one on the previous page. 2.3. Okay. Multiplexer 2.24. Okay, what we have in the previous 2.4. And I could continue. Okay, so on average, they're big. So even AutoML says big learning rates are good. So that was rediscovered essentially by our AutoML system. But of course, these are toy networks. They're not deep, and we know that. And if we try this learning algorithm with deep networks, whether the standard backpropagation or the new learning rule, they're not particularly good. And that leads us to, because of the vanishing gradients problem, of course, I mentioned at the beginning. And I argue that this problem has been studied, that solutions have been produced to bypass it, but it hasn't been solved. In other words, I don't believe that a solution, the root cause for the problem has been found, and a solution based on that being proposed, which is what the aim of the rest of the presentation is going to be about. So the ReLU function bypasses the problem. So we wonder whether we could learn something about that by evolving initialization methods using GP. But these initialization methods specifically for deep networks. Okay. So same register-based GP, we added additional input registers that have this is not a number one, it's the L, the layer number. The big L is the maximum number of layers in the net, and then there is another one over that. And the networks were 10 hidden layers with no ReLU here, standard sigmoid activation function. And so we apply this initialization rule 500 times before the run started. So 500 times of this rule, then it will stop. You will start with the standard backpropagation, and the fitness will be measured based on what the standard backpropagation achieves at the end of another 1,500 epochs. So first we initialize, then backpropagation, and we measure. Did it work or did it not? And what we found, I'm not reporting many results, but we found that our best evolved initialization method has this form. And I know it looks complicated, but what can you see here is a square here, big bracket, a square there. So what that is the gradient, the initialization gradient, if you want, that is applied to the epoch, for 500 epochs, to biases and weights. So what that means is, and it's a descent, so it's minus this that gets applied to the weights. So what it means is you start with weights that are on average 0. So the initialization is Gaussian distribution, 0 mean, small standard deviation. And then obviously, if you apply for 500 times this step, they're going to be negative. And so the net effect of this algorithm was to draw the weights to be negative. Which is crazy, right? Can't be right, we thought. But then, if you apply this initialization method, and then you apply the gradient descent, on these networks, they've got 10 and 15 hidden layers, okay? And here, before we compare multiple algorithms. We compare our algorithm, which is the evolutionary initialization method, the standard initialization method, 0 mean, small sigma, Clairaut, 0 mean, slightly sigma that depends on the number of neurons in a layer, and then Kumar, which is a lot bigger standard deviation of sigma small, in this case, variance. And what we see here is that our algorithm is not starting straight away, but within a few hundred iterations, especially on the big problems, The bigger networks, 15 layers, remember 15 layers are essentially untrainable normally. It's very quick at reaching 100% accuracies on the iris. It takes longer, backing off, 1,000 iterations on the smaller network, strangely, but the thing is, the smaller network is also narrower. So it's 10 neurons wide, while the bigger network, 15 layers, has got also wider, say 100 neurons wide. Kumar, which is the one with the big variance, manages to start and train the smaller networks, but it takes a lot longer for the bigger ones, the opposite of what we see. So it takes about 2,000 iterations to get started, and then it gets there on this problem. So we have a competitor that is not doing badly. We don't know, by the way, we don't know why using, for now, nobody knows why using bigger variances can occasionally solve the problem of certain networks. Okay. With the autoship, which is a bigger problem, as you can see, the same situation with our evolutionary method, you can get going almost immediately. With the smaller, the networks with 10 hidden layers, it takes a bit longer, but then it starts. The harder problems, you can see how the larger variance, it helps, but only much later. You need to be very persistent and believe in yourself, because you need to wait 3,000 iterations before anything happens. Or, in the case of the bigger network, 5,000 iterations before anything happens. That's DNA, a bigger problem. Again, the big networks, they really benefit from that algorithm, from our initialization algorithm. The other ones less, but they do succeed. But also, of course, Kumar. So, of course, there are lots of questions that we had. How is it possible? I mean, obviously, how is it possible that negative weights are so beneficial? Why do they help the bigger networks more? Even if it takes time for some like 500 iterations, etc., before the gradients pick up, they do pick up eventually. So they're not quite in the same situation as with the other this original initialization. So yeah, lots of questions that we try to address with a little bit of theory. Very, very simple back of the envelope theory, type of theory. So here it goes. First of all, the first assumption, because otherwise you're in real trouble, we assume to be at the very first epoch of training. So the weights have not been trained. There has not been any forward propagation yet, no backward propagation yet. And we start with weights initialized from a Gaussian distribution, normal distribution, a small sigma square, say 0.1 or something like that. But the mean of the distribution, we don't assume it to be 0. We say, well, we'll find out what it needs to be. So, of course, the net input for the neuron's particular layer will be the sum of the bias for that layer and the weighted of the neurons in the previous layer with the weights here. Now, the thing is, though, we are at the very first stage. So the activation of the weights, these are random variables. The activations will be whatever, but they are uncorrelated. And so, because of that, the expected value of this product is going to be the product of the expected values. And that leads to the mean here, we do not assume that all layers will have the same mean for now of the initial distribution. It could have been different, it could be the same. But what matters here is that from this expression, the net input, the expected net input is proportional to the mean of those weights times some factor that depends on the activations in the layer before. Okay, so that's interesting. Then, of course, there's a fact that because these variables are all random but equally distributed, and they are equally distributed because nothing has yet happened. It has been just a forward propagation of activation all of the neurons in the same layer have exactly the same distribution. For that reason, I can drop the subscript. Same for the net inputs. So I can drop the subscript here. And so this is the sum of n times the same number. And here it is. So here you see the appearance of the width, the number of neurons in a layer for the first time. We got the number of neurons here. We got the mean of the initial distribution there. And then we do a very bad approximation. We assume, so obviously activation in a layer is the squashing function for the net input for the layer. We make this wild assumption that that's the same as doing the squashing function of the expected input. Not true, but we push on and then we verify the results. So with that approximation now, we can compute the expected value of the neurons in layer, or the activation of the neurons in layer L, or this layer, based only on the expected value of the activation of the neurons in the previous layer. And yes, there is a squashing function here, but mostly the elements that I can change are this and this. So we have, this is a forward propagation, an expected forward propagation of activations. So now I want to do the other element, which is, can I do a backward propagation of the errors? Well, by definition of the error, if you know a little bit about the backpropagation, you know it's this formula here. But again, the deltas and the W's are largely uncorrelated because we haven't done any update of the W's yet. Okay, we're just looking at them at the minute. We're computing the gradients. We have done a forward propagation, but not back propagation of errors, or we've not done the updates. So again, same thing. This is the expected value of this is the product of the expected values. We assume uncorrelated. Also, this is uncorrelated. And we have it from previous results. And step by step by step, we get to the point where we have a much simpler formula on the deltas from the layer before and the net inputs from the layer before. And again, we can drop the subscript here because all of these deltas, as an approximation, all these deltas will be equally distributed past the first layer, output layer. And again, so we have a relationship that allows us to backpropagate the deltas and in an expected value, and there is a dependency on the mean of the weights and on the size of the layer. And so finally, you get to an expression that looks a little bit horrible, but what counts here, this is the first order derivative of the activation function, computed somewhere, okay? Let's ignore where it's computed, but then the rest here, the deltas, the errors are backpropagating in proportion to the product of these two things. And that allows us to then compute the delta weights, which are, of course, the product of the activations times the deltas, for those who know about the backpropagation. And eventually, it leads to this recursion to be, it's possible to unwind this recursion and this form here. So we've got this derivative times the product of the stuff in yellow. This thing here is complicated and we don't really understand it. We ignore it for now. But we know the values, the limits of this. So, but what matters is that we have the number of neurons in this layer times the mean on this layer. The number of neurons at the layer before or after times the number of the mean of the initialization of this layer, and it keeps going. So it's clear that these factors here, they can determine whether the errors are amplified or shrunk or whatever. And of course, we don't know the value of this, but we know that in the sigmoid activation function is between 0 and 1/4. So all of these terms are shrinking the gradient. So at the very least, we need to compensate. So I want to sort of move a little bit faster on this, but you can do calculations, and you find that if you can guarantee that the means, so if you guarantee that these terms, these factors here, these factors, the derivative times this mu and n, are approximately 1 or bigger than 1, then you won't have shrinking of gradients. So that leads to this formula. And then from this formula, you solve for mu, the magnitude, the mean of the initial distribution, and you take an approximation of this, you go in the middle. So because we know it's between 0 and a quarter, we go for the middle, 1/8. And then you replace, and you find this expression. And from that one, you find that the negative is the only one that is acceptable, and the positive is not. So the new initialization method that we derived theoretically is that the mean of the weights needs to be -8 over the number of neurons in the layer, which seems an absolute absurdity, if you ask me. And when we looked at it, we were thinking, yeah, right, it can't be right. Well, we proved it with the second method, because otherwise neural networks journal wouldn't accept it. But the point is, well, let's get the experiments going. Okay, so the good old auto-ship problem, so relatively big network of 15 layers. And what we see here is the mean. And we're using the same mean for all of the initialization of every single layer here for simplicity. And here is 0, here are the negative values, here are the positive values. But also we try with different sizes of the layers. So 100 neurons or down to 30 or something. Okay. Now this is what it is in layer 1. It is the layer connecting the inputs to the first hidden layer. And you can see, and here you see the curve mu equal -8 over n. So that's encouraging because we can see that the amplitude of the weights in that layer was quite big compared to other places. So okay, let's move to the next layer. Okay, similar. And the next layer, and now you start seeing something like here that it wasn't that very visible. And then you go to 4 layers from the input, and it starts forming really. Maybe the constant 8 is not perfect, particularly for this problem. Who knows? But there is something really good on the -1 over n factor. And so I move layer by layer, 7, 8, 9, and 10. Now, starting from here, we're getting closer to the output layer, so you should expect at some point to start seeing a transition, which is happening now. Now, also with the mean of 0, you can have good gradients in that layer. But if you use that mean and you move backwards in time, it would be no good. So the gradients would stop propagating for sure. And then when you get to 13 layers, etc., eventually when you get to the last layer, you can see that not only the mean could be 0, but also even slightly positive would be good. But again, as I said, what matters is that you need to find a compromise between the gradients everywhere, and you better have them at the input layers if you want the network to adjust those feature detectors, the first few layers are really feature detectors, for them to be adjusted. So on the auto-ship problem with 13 layers, we see this situation. Remember, this is similar to the plots we've seen before, where we were using the evolutionary learning rule. We were doing 500. But now look at the difference. If you initialize with -8 over number of neurons, you can see that you start straight away with both the large networks, the deeper network and large, and which are these ones actually, and with these bigger ones. But anyway, sorry, this is the accuracy, validation accuracy. This is the accuracy. While with Kumar, in both cases, you need to expand the usual thousands of epochs waiting. Same for the breast cancer, you start straight away and you're solving the problem straight away rather than having to wait for about 5,000 iterations if you're using Kumar. And of course, there's absolutely no solution coming from the standard initialization method and Gloro. I should have said that none of the runs succeeded. Same for DNA, iris, wine. Okay, so what about bigger problems? CFAR, etc. Well, yeah, here it is. We have used convolutional neural networks, 3 convolutional layers, max pooling, dropout, 10 hidden layers, followed by 10 hidden layers, dropouts, etc. 100 neurons, softmax. So, and it seems to me that it is solving the problem. And the blue lines are individual runs. So for every single seed, the standard backpropagation with the new initialization method, etc., while when we have alternatives that are at least as good as ReLU. So just as further reading, I want to acknowledge the work that Amradi did in the late, with me, of course, in the late. This is just one of the many papers, but also the Ahmed Yilmaz's thesis, where a lot of the research described here, maybe not at the same level of maturity that you've seen today, because obviously we spent a lot of time writing the papers, and I spent most of my study leave, recent study leave on that. But yeah, so a lot of information in the thesis, more information in all the theoretical models, etc., on the vanishing gradient problem here. There is a nice little piece of code that I've provided in GitHub for those interested in saying goodbye to the vanishing gradient problem. And obviously there is a larger paper on this performance measure of an optimization through computational effort that has reached the second round of reviewing in the ACM transactions evolutionary learning. And fingers crossed it should go through this time. So that's all I have. Thank you very much.
Thank you very much, Ricardo. Let's start with the round of questions. It was very interesting. Anybody in the room? Yes. Well, Sergio already has a question, so go ahead, Sergio.
Thank you very much, Professor Ricardo. It's very interesting.
Thank you.
I have a couple of questions.
Yeah.
In the plot where you are testing with different examples, accuracy appears, but also appears the p-value as function of the number of epochs.
Yeah.
What is the hypothesis that you are testing? How did you calculate the p-value?
Okay, so a key element of, so first it was very large number of runs, so 200 runs for each initialization, not for each initialization, with 200 different seeds, and we use the same seeds for different conditions. So we had paired data, so even stronger statistical evidence. I think we used the Kolmogorov-Smirnov test, or the Wilcoxon rank sum test actually. And so that's why the values are almost zero, because we've got 200 data points paired by the initial condition. So that's a question.
Yeah, thank you very much.
Pleasure.
Okay, very thank you.
Hi, my name is Tate. Thank you, Professor Ricardo, for your talk. It's very interesting. I'm not an expert, and maybe some of these questions are naive, but well, I'm going to make them. From my understanding, the new learning rules are highly dependent, or some dependent of the data set that they were learning. So, and maybe you explain how to generalize these learning rules into more complete theory or basic theoretical framework. But what do you think if you use another kind of data, or another kind of neural networks, for example, transformers, and textual data for learning. Do you think that other kind of new learning rules can arise from this kind of architectures and data?
Well, thank you for your question. So, yes, in our long article, it's an enormous article, the one that is, yeah, and it's like 57 pages with lots and lots of additional material. So we did analyze to death the learning rule because we wanted to understand the principles behind it. One element that is that it has is that asymmetries are a little bit like the same thing that is happening in the gradients with the new initialization rule. Essentially, what happens in a neural network if you initialize it with all the weights 0 mean, you're initializing the neural network in an inflection point on the surface. So because it's very easy to prove, in fact, because if you change one weight, just one weight in one direction, you can either improve or make worse the error. If you change just one and in the opposite direction, you can either make it worse or better. So essentially you're starting the network in an inflection point. And there is recent research that shows that there are, and there is old research about the competing convention problem, where essentially, I mean, I don't want to get into this, but essentially the functionality of a network is exactly the same if you permute the neurons with their weights, if you change their order. You move the neuron. If I take a neuron from a position and I move it there, take the other one down, and I move the weights together, then I'm permuting the network, but it has exactly the same functionality. But it's a different network. So if you look at the encoding, it's a different network, different matrices, etc. So there are an enormous amount of symmetries in neural networks, which mean that, and we started them from an inflection point. So it's not an optimal or a maximum or a minimum, but it's a position where you're like sitting on the saddle, basically. So I think that the reason why this rule, our new learning rule, and also the new initialization method work well is that they commit to a choice. They force you to make, they make a counterintuitive movement away from that 0. In the case of the initialization method, it of course comes from the theory and it goes negative. But anything away from that inflection point is a good thing. And I think that's why our learning rule kicks in very quickly at the beginning. But that's just, that's what I can say without drawing diagrams and doing things.
Okay, okay, thank you. I have another question.
Yes, go ahead.
The efficiency of the new learning rules, maybe, yes, is a bit more complex. It's higher than standard one. From my only seeing the expressions in the screen. So I know that it's very complex or very costly to train large neural networks. Again, thinking in transformers, thinking in this kind of neural networks. So do you think that is or can be an improvement even when you have costly expressions for learning?
So that's definitely a very good point. And I mean, everyone in neural networks use Adam, but Adam takes twice as long of standard gradient descent. But why do they use Adam? Well, because you know that in the end it converges faster. And so here the effort was, the computational effort measure, for instance, has been based on the effort in terms of gradient descent steps. But of course, as you correctly noticed, if a rule is more complicated, it would take longer to execute. Now, of course, we could have defined the computational effort at a finer grain. So we could have counted how many atomic operations you need to do that gradient descent. And then it's another valid way. And then maybe the comparison could look different. I'm not denying that, but it would still be a rigorous way of doing it. So, and I can't say for sure, because you can count the opcodes, but actually GPUs are so fast that executing those opcodes may take executing 6 or 7 opcodes may take a fraction of just a fraction longer than executing 3 or 4, because even the standard gradient descent has 4 multiplications, etc. in it anyway. So it's a good question, and all I'm saying here is that we need, if you define a rigorous measure, and you can also talk about, oh, wait a minute, I've got parallel architecture, and I consider the fact I'm running this run sequentially. So, but if you go a big parallel architecture, maybe you can also consider the parallelism itself. So it can become richer and more articulate, and then we would see. But I think it doesn't matter if the new learning rule will be overtaken by other things, but what matters is that we have a rigorous way of doing AutoML now, rather than where we know what we get at the end of it. You're just not hoping that it will get some acceptable value. We're just guaranteed to get an acceptable value of accuracy or loss. I hope this answers your question.
Yeah, thank you. Okay. Anyone has another question? I do have one question, Ricardo. Can you explain a little bit how to implement the not the learning rule, the initialization method? I understand that it was -8 over n, but then I got confused about what is n.
N is the number of neurons in a layer, the layer where you're considering. Yeah. The way, if you look at the code in GitLab, I've defined for Keras a small randomizer initialization that you can directly use in your normal Keras, and it will count correctly the number of connections in a layer, including convolutional layers and all of that. So you can, shall I paste here the URL or something? Also, I can paste the URL. Let me find out how to do it. Okay. So is there a chat where I can do?
Yes, there is a chat where you can put something. Let me just put.
Yeah, I think this is GitHub code. This one. So if I can share the screen once more and just click on it. Maybe not. Let's avoid the damage, because I might not be able to. Might have to log out. It's about, I don't know, 50 lines of code, and the initialization itself is probably 15 lines of code. A small class, a small initializer that will do the right thing.
No, it's all right. I can look at it, and just now that you told me that n corresponds to the number of neurons in the layer that you are in, then everything is all right. And the other is a curiosity on when you were evolving the new learning group, the data set were normalized. The inputs, the features of the problems were normalized to have something like 0 mean or 1 standard deviation or something like that.
So you're talking about the inputs of the, or you're talking about the error measures at the end in the fitness evaluation?
No, the inputs of the problems. For example, the iris problem. The inputs were
I think, from memory, I think they were normalized to avoid, obviously, some of those problems got enormous numbers, others small. So, of course, you need to make sure that you're not, unduly worsening the performance. There are subtleties, interesting subtleties by which, for instance, and they're explored a little bit in the thesis, because for the input layer and the output layers, you might want to consider your data set to set the mean values of initialization. I don't have time to elaborate here, but so if you had the features were incorrectly scaled, but the initialization was correctly done, it would still be okay.
Okay.
Yeah, but the mu would depend. Yeah, it does depend on the mean input value. But for simplicity here, we're providing a very simple rule that kind of works. But it could be we've even evolved the mu values for different layers to see whether they converge. And by and large, they do converge to the ones predicted by the theory, except for the input-output layer. In some problems, they need to be different values. Precisely because the input set may have a much bigger mean than or might be zero scaled, so that everything is zero mean, or might not be, and so there is a slight dependence on that as well.
Perfect. Thank you. Well, is there any question? Well, thank you very much, Ricardo. It's late for you, so thank you very much for again for accepting our invitation, even though that it's I don't know, almost 8 or 9 when you are.
No, it's only 7:20, but thank you very much. It's been a real pleasure, and it's forced me to sort of put down these ideas in one place, and so thank you very much.
Thanks a lot.
Bye bye.